Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to look at an example using the Euler method for a first-order ordinary differential equation, and we'll look at one where we can compare to the actual solution. Now, as a reminder, the Euler method basically takes the forward difference representation for the derivative, and you solve for the y of x plus delta x piece. And if we use a notation where the subscripting represents I, means I'm talking about point x, my initial value we'll call it, plus 1 times delta x. So 1 delta x step away, and delta x is our step size. And so we get y of I plus 1 is y of I, so a previous guess, plus delta x times the function evaluated at x and y. We want to apply it this time to an example. We're just going to do dy dx equals 9.8 minus 0.196, where y at when x is 0 is 48. And we want to do this using a couple of different step sizes so that we can get a feel for the precision on these answers. What kind of accuracy am I going to be able to get? And then also we want to be able to compare for the actual solution, which in this case is 50 minus 2 e to the minus 0.196x. If we use our formula, we see that y of I plus 1 is yi plus delta x times 9.8 minus 0.196 yi. We're going to look at our accuracy here, but generally the error is going to be on the order of our delta x step size. In this particular case, because this is a nice function, as long as I stay fairly close to my initial value, it's going to actually be much smaller than that. But we're going to take a look at this. I don't normally have the luxury of knowing the answer. So what we typically do is we will try our various accuracy, or try for a step size, and then keep cutting the step size in half until I see one where I don't really get a lot of change. And in that case, I'll say, okay, then I'm good enough and I'm done. So let's now look at this in Excel, because really that's the purpose here. So in this particular case, what I want to start with is a first guess of x and y. And I know that when x is equal to 0, y is equal to 48. And my x's I'm going to change by step size 0.01. So it's equal to this plus I want to point to that because I'm going to want to change it easily. All right, so I've taken my x plus the step size there. And my formula says that y of I plus 1, so y at the next step, is equal to y at the previous step plus the step, okay, did that wrong. Okay, so it's equal to this plus, now we got the plus sign in there, delta x times the function at my x and y from the previous line. My function is 9.8 minus 0.196 times y. Okay. So it's a little bit bigger than 48. That makes good sense. All right. I want to be able to just duplicate these down. So in order to do that, I want to use relative references for the previous x, but I want to use absolute references for the step size. So on the B2, I'm going to insert dollar signs. I did that using the F4 key. And same thing for this one. For the delta x, or my step size, I want to use absolute references. And so now I can take this and copy it as far down as you want. Okay. Now I want to compare this to the actual. And in this particular case, I know the answer. It's 50 minus 2 times the exponential of negative 0.196 times the x. And when I type that in up above, I see I left out the minus sign. All right, so that's good. And again, I want to copy this, and I can. All right. And you see, this really doesn't look like it's too bad. Okay, I would be happy with this as an estimate of the function. And we can graph these if you wish so that you can get a better view, but we also can look at a percent difference. And so that would be taking, well, it doesn't really matter which direction you do, but okay, I'll take the estimate minus the actual divided by, and you want to do the actual. And I want to make it so that it's a whole number, or not a whole number, a number greater than 1, so 100%. Oh. Okay, so my percent differences are very, very small in this particular case. And it's because it's a well-behaved function, and I didn't go that far away. But remember, we said we wanted to look at other step sizes. So if I look at 1, for instance, now I see that my percent difference is much larger as we go through this. But I could just keep reducing my step size until I feel like, so let's, keep an eye on 1. So 48.707 at 2. If I cut this by 1/2, 48.707, okay, so that was a pretty good change in my answer there. Let me cut that in half. And at 2, 48.66. Oh, that's getting a little closer. If I go to 0.125, if I literally want to cut this in half again, then at 2, 48.655 instead of 0.66. At this point, I feel pretty good, like this is going to be good enough. And so that's the idea of how we can keep reducing step size and just pick a particular point and keep looking at that and compare the answer. And if it doesn't change too much, then you can call that good enough. But again, the idea is I start with a fixed value of x and y, and then as I march away from this and using my step size, as I march away, I'm going to calculate the y at those values also. Now, we also want to be able to do this in VBA. I'm going to do that as a separate video lesson, and then we will look at one other example so that we can get a better indication of the accuracy. Thank you very much for your time.